Topic 2.6 is called competing function model validation, which is a lot of fancy words to say we're working on making sure we're choosing the correct function type when presented information. Now, we've done this before when we were given tables. We checked the rate of change, the change in the rate of change, or if the outputs are changing proportionally. And all of that stuff is still good. These are the three types of functions we've worked with really so far in this class. I know polynomial was all of the types of polynomial, but if we focus just mainly on quadratic, we have the following information. We can look at a data table. We can see that the outputs are changing at a roughly similar or constant rate of change. On a graph, we would see, oops, my Apple Pencil is dead. That's what I get for not charging it over the weekend. We can see that the dots all line up in a generally linear pattern. And if we were using vocabulary from this class to describe a linear function, we would say that it has a constant rate of change. Not it, sorry, don't use the word it. The output values have a constant rate of change over equal length input value intervals, or at least relatively constant. That would give us a linear function. For a quadratic, we can see in the table that the numbers are changing with a constant change in the rate of change, sorry. The dots on a graph would make a parabola, would make a U or an upside down U shape, a happy parabola or a sad parabola. The words we would use to describe this is that over equal length input value intervals, the output values have a constant change in the rate of change. Again, we've written this sentence many, many times, so we've been doing this validation where we decide which works best. And then, of course, we learned most recently about our exponential, where we noticed that the pattern, the outputs are changing with multiplication or division in a consistent way. The dots would look like basically half of a parabola that don't go back up, which is your growth and or decay exponential. The words we would use here is that the output values change proportionately. Again, all of this is familiar, and we do this a lot when we have nice tables. But the thing is, some of these tables are not nice. If you actually went through and found the differences in these tables, they're not actually consistent, but they're relatively consistent, which makes it kind of hard for us to be confident in how we would choose the type of function that represents data. So instead, what we have done in the past, probably in other classes, is you plot all of the points and you just look at the shape. If all the dots line up generally going up like this, see how they're not perfectly in line, but they generally go up in a linear fashion? Great, we'd call it linear. We could call it quadratic if it looks like quadratic, or exponential if it looks like exponential. But there's another way to do this. There's another way for us to validate if our model, our function equation that we created, is the best model, and it's through the use of what's called residuals. So go ahead and flip it over. That front page is just kind of a review of the vocabulary all on one page. But residuals here are what we're going to do to verify that our information is valid, that our information is not just like some silly prediction. Residuals are used to predict, models are used to predict values for the dependent variable or output when you plug a value in. Yes?
Is that pink or purple?
That is pink. Thank you for asking. I'm colorblind. When using a model, it is important to remember that this is only a predicted value from our equation, not an actual data value from the actual information we have. So if we use an input value that is a known data point, an actual data point, to find a predicted output using our model, the difference between the actual output and our predicted output is called the residual. You can think of this as like the error. So if we know what actually happened at time 3, and we also have a prediction of what would happen at time 3, we want them to line up because we want our models to be really, really good. But sometimes there's error in the real world versus our math world. And so that is called the residual. If we're highlighting this, our residual is equal to the actual output value minus the predicted output value. If you're Googling for this later, a lot of times people write this formula as y minus y hat, which you've never seen the notation of a y hat before probably, but it looks like an up caret sitting on top of the letter, and it's literally called a hat. So that's y minus y hat. So if you're Googling for this later and you see that, that is what I'm talking about. We're just going to use words and we're going to call it actual output value minus predicted output value. And it creates our residual or our error. It helps us know how good our model or how good our prediction is for this particular scenario. So for example, let's say we have this problem that says the weight of newborn babies can be modeled by a linear function. What type of function? Always look for function type. For the first 4 months after birth, the selected values for the weight, WT, in kilograms of a particular newborn baby are given in the table on the right, where T represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model. What kind of model? Specifically in the form WT equal to A plus BT for the weight of this baby T months after birth. So that's telling us to use our stat edit feature on our calculator. Right now, I believe the last class that used these was my dual credit class and they were taking a test. So honestly, clear your calculator before you do anything because they changed a bunch of settings that you don't want. So please make that a habit for yourself when you pick up my calculators because the class before you changes the settings. But then I want you to take this table and put it into stat edit. And I want you to create this regression for me. Now make sure you actually use the correct regression. Notice here, it's not y equals mx plus b, it's a plus bt or b plus mt. So it's not slope first, it's actually y-intercept first, which is not option 4 on the calculate menu. But I'm gonna let you think because I see everybody working, so we know what we're doing. Fabulous. So we ran the regression using option 8 to match the function type in the problem, and we got that our function, our model, should be WT equal to 3.34 plus 0.8 times T. Yes, that's a review from before. Always work with regressions. Make sure you use the correct function type. Yeah? That's a great question. You go to mode and you turn the stat diagnostics on. Go over to where it says stat diagnostics and click on. Yeah, there it is. Okay. Sounds harder than it is. Fabulous. Now, part B says to use the model found in part A to predict the weight in kilograms of this baby 2.5 months after birth. So if they gave me 2.5 months, did they give me a time or a weight? Time. Very good. So that means we're going to plug it in. Basically, this is asking me to do W of 2.5, but we're going to work smarter, not harder. So since we already stored this equation in our calculator, we can type on the home screen y1 open parentheses 2.5, and that's telling our calculator to plug the number 2.5 into our function. This is especially great when we would have had to round the values for A and B. This one we didn't have to because these were nice values for A and B, but if you round, you especially don't want to use the rounded values to the very end. So if you would please, in your calculator on the home screen, so the regular typing screen, you press alpha trace enter parentheses 2.5 close parentheses enter. What do you get? 5.34. Amazing. So we predict that the weight of this baby at 2.5 months is 5.34 kilograms. That is our predicted value. We have used the model to predict the future.
What would that be in pounds?
I don't know the conversion off the top of my head. I will be honest.
10 pounds for a 2-month-old baby.
Isn't it like 1.5 pounds for 1 kilo?
I would straight up Google that, honestly. I don't know. I am really bad at conversions, like, off the top of my head. Anytime I cook, I have to Google, like, cups to quarts. And I, like, feel like I should be able to do that at this point in my life, but it's my weakness. Okay. Part C goes on to say, the actual weight of this baby 2.5 months after birth was 5.5 kilograms. Notice, that is the actual weight, not the predicted weight. The question says, what is the residual for this weight prediction? Did our model underestimate or overestimate the weight of this baby 2.5 months after birth? So here's what we're going to do to find the residual. We know that a residual is found by doing the actual value minus the predicted value we got for the same input. So at 2.5 months, we weighed the baby. They were 5.5 kilograms, but we had predicted 5.34 using our formula, which means that our residual here is 0.16. That's the residual value. That's the error in our model. Now, did our model, the pink number, did it over or underestimate the weight of the baby? So our model, we're going to write a little sentence, our model underestimated the weight. Cool. Underestimated. Fabulous. Part D and E are for you. You already have the equation for the model. I want you now to predict the weight of the baby 4 months after birth and then answer part E. Let's see how we did. So if we're using the model found in part A to predict the weight of the baby 4 months after birth, that's like asking for W of 4, or in our case, Y1 of 4, because we have our W equation typed into Y1. And did you get 6.54 kilograms? Amazing. So we know that this is our predicted value for 4 months. The question E says, what is the residual weight for this weight prediction? And did our model over or underestimate the weight of the baby 4 months after birth? It didn't tell us what the baby was weighing 4 months after birth. But we have that information up here. In the table, we have the actual weight of the baby after 4 months. We can see the actual value in the table. So we do actually have that actual weight. So our residual here is going to be 6.4 minus 6.54, which if you calculate, that is negative 0.14. Yes, your residual can be negative. So what does this mean for us? If we look at the number we got as our prediction versus the actual, did our model over or underestimate? Over. Our model overestimated. And not by much. Like, that's not a big difference in numbers, but for baby weights, that is pretty substantial. Yes, yes. Now here's something, before you flip the page over, I need you to make a connection here. We got a positive number for our residual, and we said it underestimated. What happened when we got a negative number for our residual? Interesting. So what that means for us is if we were to graph the residual values for each data point, flip the page. If we were to graph a residual plot of the input values and the residual value or the error, what that means for us is these residual plots will show us which data points over and underestimated different things. So since our residual data is always going to be plotted as input value, comma, residual, every data point that is above 0 has a positive residual, which means that all of the predicted values above 0 are underestimates. And all of the values with a negative residual underneath 0 are overestimates, which looks a little backwards since the under is above and the over is below. So got to keep that straight. Positive residuals are an underestimate. Negative residuals are an overestimate. So the graph has underestimates above 0 and overestimates below 0. But these residual plots, while we could make them, the most important thing I need us to do is be able to look at them and decide if it validates our data. So a residual plot, when it is graphed for our model, especially when we're competing with different models to validate which one is best, if a model for a given set of data is appropriate, the residual plot should appear without pattern. I know I highlighted that, but I want you to circle the words without pattern and like draw an arrow to them and put a bunch of exclamation points. There should be no patterns in our residual plots if our data uses the correct model. If there is a pattern in the residual plots, like they look like they're going all uphill in a linear fashion, or sinusoidal, or they're looking like, y'all don't know what sinusoidal is, wavy, okay, or a quadratic, then that's a not appropriate graph. It needs to kind of look like super random, horizontal bunch of equations, okay? So if we're looking at example 2, it says, an exponential regression was used to model a data set The residual plot was created for the exponential regression model, and it is shown on the right. What is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? Does this look pretty random to you?
Yeah.
Does it look like there's a pattern to the function? No, which means we can make the following conclusion. We would say an exponential model is appropriate because the residual plot shows no clear pattern. If there is a pattern in the data, you picked the wrong model, basically. You got to try again. If the error is pretty random, that means we did a really good job drawing the line of best fit or the curve of best fit. So it's appropriate. So another way this question might be asked is going to ask you to compare plots. So in example 3, a group of AP Pre-Cal students used a set of data to create a linear, quadratic, and exponential regression models. So here's the linear, here's the quadratic, here's the exponential. After creating the 3 models, the students created residual plots for each model type, which is what's below. Based on the 3 residual plots below, which model is most appropriate for the data? Which is the one that shows no pattern? The last one, the exponential, because this looks like a clear pattern to me. This looks like a clear pattern to me. But this is like jumbled. That's what we want. So we want to write the following sentence. We'd say, based on the residual plots, an exponential model is most appropriate since the plot shows no clear pattern. So residuals are a way for us to look at our error in our models and decide if we picked the right function type. The same way maybe you would have plotted all of the points to see what the shape looks like, you can also do that with a residual graph, which is the plots. You just need to make sure there is no pattern to these errors, to the residuals. Before we read example 4, are there any questions about a residual plot? No clear pattern is good. Now, one more time, before we read number 4, pull your attention back to this graph right here. Remember earlier we said if our output value is positive and it's representing a residual, that was when we underestimated the data, so it goes above. And if our residual value is negative, it underestimates the data. If we look at example 4 now and we read it, it says, students in a pre-calculus class measured each student's height and arm span in centimeters. The students calculated a linear regression with heights as the input values and arm spans as the output values. Given the residual plot has a point labeled P at the coordinates 175, 23.4, what does point P indicate in the context? So remember, with coordinate points on residuals, this is the input value. So for us, the input value is the height, and the output values are my residuals in a residual plot. So since my output value, my residual, is positive 23.4, on a graph of a residual plot, would this dot be above or below 0? Above. Does that mean that it's going to over or underestimate the data? Underestimate, which again feels backwards because it's above, but that means it's an underestimate of what the actual arm span for somebody that's 175 centimeters tall.
That's like 5'10".
175 centimeters, so it's 1.75 meters, so that's, yeah, about 5'10". Again, conversions is not my strong suit. I can do it on paper, but in my head, not great. Beep. Okay, questions about these error analysis. So again, when we started this, what we did to check the type of function we should use is look at the tables to see the patterns. But if the tables show no pattern because they're like data points and not pretty mathematical numbers, we can use residuals to decide what kind of model is best for our data.